Hello everyone, I'm Taegeon from Samsung Research Data Cloud Lab. Today I'm going to talk about Metis, Fast Automatic Distributed Training on Heterogeneous GPUs. This work is collaborated with my colleague from Samsung Research and Jeon from UNIST. Okay, let's get started. Nowadays, the size of the learning model increased up to billions of parameters. So it is inevitable to train the model across hundreds or thousands of GPUs. So for parallelization, the model is pipelined with multiple stages, where the number of stages represent the degree of pipeline parallelism. Then multiple GPUs are grouped as device group, and each device group is allocated to each stage to execute the layers. And the layers within a stage can be copied across GPUs within a device group, or can be partitioned with tensor parallelism. Also, input data can be further partitioned across GPUs with data parallelism. Such data and tensor parallelism is called intra-stage parallelism because they are partitioned within a stage. And since each stage can have different intra-stage parallelism, the data resharding is required to match the shape of output and input data between stages. And as you can see, there are so many knobs for deciding distributed training, such as creating stages and device group, and assigning device group to stages, and deciding the intra-stage parallelism, and so on. And the performance of training significantly vary according to the plan. So it is really difficult to find the optimal parallelism plan that minimizes the training time. Therefore, recent work such as ALPA propose auto-parallelizer that automatically find efficient parallelism plan on homogeneous GPUs. Meanwhile, new types of GPUs are released every few years, so the GPU cluster contain different types of GPU, which we call heterogeneous GPUs. In heterogeneous GPU cluster, usually the number of available high-end GPU is small because of its high price and high demand, whereas the number of available low-end GPU is large, and most of them are idle because of its low price and low demand. Therefore, instead of using the small number of high-end GPUs for distributed training, fully utilizing both high-end and low-end GPUs altogether can improve the training speed and also improve the GPU utilization. Therefore, in this work, we focus on designing auto-parallelizer on heterogeneous GPUs. However, as existing work is designed for homogeneous GPUs, they fail to find efficient parallelism plan on heterogeneous GPUs. To illustrate this, let's assume that there are two types of GPU, V and A. Then the existing work abstracts the heterogeneous GPUs as homogeneous one, which is represented as R in this figure, by profiling and averaging the performance of heterogeneous GPUs. And after this abstraction, the remaining process of auto-parallelizer is all the same as in homogeneous GPUs, such as creating device group and stages, and pairing the stages with device group, and deciding intra-stage parallelism, and so on. So as you can see, this abstraction simplified the system design because we don't have to modify the existing components of auto-parallelizer, but it has several limitations in finding efficient parallelism plan on heterogeneous GPUs. First, they have limitation in exploring diverse device group. For example, when there are two types of GPU, V and A, and there is an abstract device group with two R GPUs, then the number of possible mapping of GPUs to the abstract device group is 4, such as VV, AA, VA, and AV. However, the existing work just explore one mapping based on the rank and order of GPU because they assume that all GPUs are the same. Therefore, they do not explore the remaining mapping of GPU and fail to find more efficient pair of stage and device group on heterogeneous GPUs. Second, they have limitation in load balancing. To illustrate this, let's assume that there are two stages, and the stage 1 is assigned to two V GPUs, and the stage 2 is assigned to 2A GPUs. In this mapping, the optimal layer load balancing is to allocate more layers to stage 2 than stage 1 because the computing power of GPU A is higher than that of GPU V. However, the existing work just evenly balanced the layer across stages based on the number of GPUs because of the homogeneous GPU abstraction. As a result, they failed to find more efficient load balancing plan on heterogeneous GPUs. Third, they have a limitation in exploring diverse cluster shape. To simplify creating device group, the existing work assumes that the number of available GPUs per node is all the same. So they abstract the GPU cluster as two-dimensional grid, where n is the number of nodes and m is the number of GPUs per node. However, this two-dimensional abstraction can be broken if some of GPUs are being used in a node or the number of GPUs per node is different. This situation is more prevalent in heterogeneous GPU cluster than in homogeneous GPU cluster because of the heterogeneity in the GPU demand and the number. Therefore, they must wait for a long time to execute a discrete training job on heterogeneous GPU cluster until all GPU nodes have the same number of available GPUs. So to solve this limitation, we propose Metis, a system that automatically finds good parallelism plan on heterogeneous GPUs. Instead of abstracting the heterogeneous GPUs as homogeneous one and the GPU cluster as two-dimensional grid, Metis expands the search space of plan by being aware of heterogeneous computing, memory, and the number of GPUs. As a result, Metis can explore efficient parallelism plan that the existing work does not cover on heterogeneous GPUs. So to illustrate this, let me briefly show the overview of Metis. For automation, Metis consists of 4 components: profiler, cost model, planner, and runtime. The profiler profiles required metrics from heterogeneous GPUs separately, and the planner then explores various plans on the expanded search space and find the best one based on the cost model. Whenever the plan is provided by the planner, the cost model estimates the execution time of a training job using the profiled metrics. Once the best plan is selected, the runtime executes a training job on heterogeneous GPUs based on the plan. And obviously, the key technical challenge in designing Metis is to reduce the huge overhead of profiling and searching that may take several days or weeks on the expanded search space. Therefore, we design an efficient profiler and planner that reduce such overhead to quickly find near optimal plan. In this presentation, I will focus on describing the detail of the planner, which is the core components of Metis. So please take a look at the paper if you're interested in the details of profiler and cost model. So in the planner, to reduce the huge search overhead, we developed 3 techniques by harnessing the characteristics of distributed training. The first one is pruning inefficient and similar combinations of stage and device group pair. And second is balancing layers across stages with capacity-aware allocation. And the last one is navigating efficient intra-stage plan based on the characteristics of data and tensor parallelism. And so in the next slide, I'll talk about the first technique. Since the number of possible device groups increased in heterogeneous GPUs, the search space of finding efficient stage and device group pairs is also significantly expanded. For instance, when assigning 4 different device groups to 4 stages, the possible number of stage and device group pair is 4 factorial for each set of device groups. And this could be n factorial if the number of stage and the different device group is n. So to reduce the overhead of finding efficient stage and device group pair, we harness the key fact that allocating stages to the imbalanced size of device group will not be the optimal solution because of the imbalanced intra-stage communication overhead. If a stage is assigned to a device group with high number of GPUs, then the stage will have high intra-stage communication overhead. As a result, this stage could be the bottleneck and generate pipeline bubbles in executing the pipeline, which degrade the training performance. In contrast, if the size of device group is balanced, the intra-stage communication overhead is also balanced. This can minimize pipeline bubble and generate more efficient stage and device group pair. Therefore, Metis prunes highly skewed size of device group to filter out inefficient stage and device group pairs. Furthermore, Metis filter out stage and device group pairs that lead to similar performance. For instance, when assigning 6 device groups to 6 stages, where 5 device groups are the same and only 1 is different, as shown in this figure, the possible number of combination of stage and device group pair is 6. However, if the model has repeated layer, then assigning the device group 6 to stage 3 or 4 will lead to similar performance because the stage 3 and 4 will have layers with same computational load and same input-output pattern. So in this case, Metis consider that the 2 plans are duplicate and filter out them to quickly find efficient stage and device group pairs. So once the stage and device group pair are decided, then next Metis decide layer load balancing across stages. In fact, naive allocation of layers to stages require cubical time complexity with dynamic programming. So to reduce the search overhead, Metis calculate the relative computing power of each stage and device group pair. To calculate the relative computing power between stages, Metis estimate the execution time of running a model on each stage based on its intra-stage parallelism and profiled metrics. For instance, when the stage 1 is assigned to the device group with 4 free GPUs, and it has the intra-stage parallelism with 2 DP and 2 TP degree, then the estimated time of running a model on the stage 1 is 10 seconds. And similarly, the stage 2 is estimated to take around 5 seconds to execute the model. Then we can compare the relative computing performance of the 2 stages, and in this figure, stage 2 has 2 times higher computing power than stage 1. Based on this, Metis proportionally allocate the load of layer across stages according to the relative performance. So by doing so, Metis can reduce the layer load balancing overhead from cubical time complexity to linear time complexity. After layers are allocated to stages, the final step is to decide the intra-stage parallelism. To reduce the search overhead of intra-stage parallelism, we also harness the key observation that increasing data parallelism is better than tensor parallelism within a stage because tensor parallelism has higher communication overhead than data parallelism. Therefore, Metis tried to maximize the DP degree as much as possible within a stage, and if there is no OM exception, is estimated based on the profile data. Once out-of-memory exception is estimated, Metis then increased the TP degree while decreasing the DP degree to reduce the memory pressure by slicing layers across GPUs. And also explore different strategies by keeping the current intra-stage parallelism and rebalancing the layers across different stages to mitigate the memory pressure. This search process is executed in the DFS order to collect possible candidate of efficient intra-stage plan while filtering out inefficient parallelism. So with this optimization, Metis can quickly find a good parallelism plan that leads to near optimal performance. To show the effectiveness of Metis, we compare Metis with 2 state-of-the-art autoparallelizer, AMP and Alpha. We test various combinations of heterogeneous GPUs, such as NVIDIA P100 with T4, and T4 with V100, and P100 with V100. Also, we evaluate the system with 3 different large models, such as GPT-3, MOE, and wide resonant. For each model, we increase the number of GPU as well as the size of model to show the scalability of distributed training. And as you can see in this graph, Metis improved training speed by 2.7 times in average and up to 8.4 times because it generates better parallelism plan than the others by expanding and exploring more plans on heterogeneous GPUs. So to show the detailed reason of performance improvement, let's take a look at the best plan generated by Alpha and Metis in GPT-3 on 16 GPUs with T4 and V100 GPUs. The first difference between the plan is that Metis has higher DP degree in intra-stage parallelism than Alpha because Metis prefers data parallelism over tensor parallelism in intra-stage plan. The second difference is layer load balancing. In Metis, layers are distributed based on the relative computing power of stages, whereas Alpha balances layers based on the number of GPU in each stage because of its homogeneous GPU abstraction. These 2 differences lead to the performance gap between Alpha and Metis. And in MOE model, the layer load balancing is also different as in GPT-3. And one more key difference is the mapping of stage and device group. In Alpha, the first stage is assigned to a device group with 8 GPUs, where 4 GPUs are V100 and 4 GPUs are T4. However, each GPU within the stage 1 will process the same computational load because Alpha assumes that the underlying GPUs are the same. As a result, the V100 GPUs, which have higher computing power than T4, are being idle waiting for the T4 GPU for gradient computation. In contrast, Metis creates device group, each of which consists of homogeneous GPUs, and balance the load across stages by being aware of the heterogeneous computing power. But please note that Metis also explores device groups consisting of heterogeneous GPUs like the stage 1 in Alpha and balance the intra-stage load by configuring different mini-batch sizes to heterogeneous GPUs. But in this example, Metis just select the plan shown in this slide as the best one based on the cost comparison. While finding the better parallelism plan, Metis also has low searching overhead. Compared to Alpha, Metis finds better parallelism plan more than 100 times faster. Moreover, compared to Oracle search that explores all possible parallelism plan without optimization, Metis search is faster by several orders of magnitude. We also compared the plan generated by Oracle search and confirmed that the performance gap between Oracle and Metis is less than 5%. This result indicates that Metis quickly and efficiently finds a near optimal solution among a huge number of heterogeneous plans. So, in summary, we show that the existing autoparallelizer is not optimized for distributed training on heterogeneous GPUs. So we designed Metis, a system that automatically finds a good parallelism plan on heterogeneous GPUs by expanding the search space. However, because of the huge search overhead, we developed a new hetero-aware search algorithm that develops several techniques. And we evaluated that Metis improved training speed by up to 8 times with less search overhead compared to state-of-the-art autoparallelizer. And we believe that Metis can be adapted to improve training speed and also GPU utilization and used for cost-efficient distributed training on heterogeneous GPU cluster. Okay, this is the end of the slide, and thank you very much for your listening.